and that is Pierre Lanari. So Pierre is going to kick off our workshop with this talk about thermodynamic databases. Pierre is an assistant professor at the Institute of Geological Sciences at the University of Bern in Switzerland. He obtained his bachelor's degree from the University of Savoie in France, and his master's and PhD degrees from the University of Grenoble in France. His research interests are diverse, as you can imagine. They involve computational petrology, in particular, development of thermodynamic databases, and the development of phase equilibrium modeling techniques like bingo antidote that he'll be telling us about later in the week. Thin section mapping and analysis software. This is the XMAP tools that he'll talk about on Friday. Modeling fluid rock interactions and determining the conditions and tempo of metamorphic processes. So I would like to welcome Pierre to take over the screen and start with his presentation on thermodynamic databases.
Okay, wonderful. Thank you very much, Dave, and thank you for the introduction. Welcome everyone, and hello. It's a great honor to open the workshop with this first talk on the thermodynamic databases. So my objectives for this lecture are to help you to understand each part of a thermodynamic database, to try to give you a detailed overview of the current offer in terms of thermodynamic databases and modeling programs. Then I will try to explain some of the remaining challenges behind the databases, for example, internal consistency and the evaluation of the uncertainties, and we'll try to target future needs and some research directions. On some slides, you will see this symbol, and if you see this symbol here, it means that as a beginner or novice in metamorphic petrology, you might be interested to understand the concept that is presented on this slide. So if you do not, please feel free to ask a question just after the talk. I will go through a quick introduction and then talk about the two parts of a thermodynamic database, the internally consistent data set and the set of activity models. And then I will describe a few limits or a few challenges in the current thermodynamic databases and give some perspectives. But as Dave already mentioned, I want to start with a reminder that what we use in phase equilibrium modeling are the scientific models. And scientific models are always imperfect. They are idealized, a representation of a physical system. So by definition, all the models are wrong. They are not the reality, and they would never be the reality. On this diagram, you can see on the left side the real world with the natural processes. And by making observations and experiments, we can extract data from the real world. Then on the right side of this diagram, you see the models of specific processes, and those are based on theory, assumptions, and calculations. And ultimately, you can do some predictions with those models. And the predictions might agree or disagree with the data from the real world. And that's the topic of the second part of the workshop. But for now, and this morning, I want to focus on the data feeding. How do we train the model to try to reproduce the data that we obtain using experiments? I also want to show you, and I think that's one of our main goals in this workshop, to demonstrate that the models that we use, they are not black box. They should never be used as a black box. They are based on theory, for example, equilibrium thermodynamics. They have some assumptions. For example, you assume that the rock that you want to study or the system has reached this state of equilibrium, so the minimum state of energy. And there are some calculations, for example, to calculate this minimum state of energy. In metamorphic petrology, let's consider for a moment that we can simplify metamorphism. We assume that metamorphism is completely controlled by equilibrium thermodynamics. And then we can simplify to a simple sketch with the causal factors of metamorphism, temperature, pressure, and the bulk composition of your system. And for those causal factors, the system will try to minimize its internal energy. And to do that, it can change the mineral assemblage, The mineral mode means the mineral fraction, the volume fraction of your mineral in the system and their composition. So those are the consequences of metamorphism. And we have developed two main modeling strategies to try to investigate metamorphism. The first strategy, it is an inverse model that starts from the mineral composition. It's not based on the minimization of internal energy. And from those mineral compositions that you assume to be in equilibrium, you try to reconstruct the causal factors, temperature and pressure conditions. There are software solutions for that, for example, for multi-equilibrium thermobarometries, such as Thermocalc from Roger Powell and WinTwig from Rob Berman. On the other direction, you have the forward models, and in the forward models, you fix the causal factors and you try to determine the consequences of metamorphism, the assemblage, the modes, and the mineral compositions. Example of that, mineral assemblage diagrams, also known as phase diagrams or pseudo-sections, and you have several programs to generate those diagrams: Thermocalc, Tariq Domino from Christian de Capitani, and Perplex from Jamie Connolly. And that will be the topic of the next 3 lectures during the workshop. But here, as I have seen, the process involves energies and it involves equilibrium. So the equilibrium condition in a system is the minimization of one of the several energies in your system. And for us as geologists, it is very convenient to use the Gibbs energy because the Gibbs energy is minimized at equilibrium for fixed pressure and temperature conditions. But the problem is we cannot quantify the amount, the quantity of Gibbs energy for a given system, because this would require to sum up all the microscopic interaction in your system. But what we can do is we can define the Gibbs energy with respect to a reference state. And it has been demonstrated quite early that one of the easiest way to investigate metamorphism is to use the apparent Gibbs energy. And here is the definition of the apparent Gibbs energy of a phase. That's the delta Ag at any pressure and temperature condition. And it's simply the sum between two terms, the standard Gibbs energy of formation of the phase at any given pressure and temperature condition, plus an activity term that is the RT ln the A being the activity or the activity of the phase in the solution. So as you can see, there are 2 parts in this equation. So the first part, the standard Gibbs energy of formation of a phase, this is a composition independent term. You can calculate the formation Gibbs energy at any pressure and temperature by using the formation enthalpy at P0 and T0, usually room conditions, 1 bar and 25 degrees C. This is the H0 minus T multiplied by the S0, the formation, the standard entropy. And then you have several integral terms. First, the heat capacity with the Cp and a volume term. The second part of the apparent Gibbs energy equation is the RT ln the A. This is the activity of the phase in an hypothetical solution. It's a composition dependent term. And for example, if we assume an ideal activity with P, the proportion of the phase in the solution, we can simply have this term, RT ln the P. So as you can see, if we want to calculate the apparent Gibbs free energy of several phases, all the phases that we have in the database, we need to know for each phase the values of H0, S0. We need to have a Cp function, a volume function, and some activity terms. And those are the 2 parts of a thermodynamic database. So you will hear a lot about thermodynamic database. And the definition I'm giving here is that a thermodynamic database is made of a data set that contains some standard state properties, for example, values for the enthalpy of formation, the standard entropy, and some parameters for the heat capacity function and the volume function. So with the data set, you can calculate the composition independent term for any phase in the database. And then on top of that, you need a set of solution models that are compatible with the data set, and they are used to calculate the composition dependent term here in the equation, depending on the composition of the solution. It can include ideal or non-ideal contributions, as we should discuss in the following parts. But now I want to try to give you an overview of the existing databases and software solutions. And this is a quite challenging task. So I decided to draw a map of the principal thermodynamic databases and modeling tools. So I divided the notion into two parts, the metamorphic petrology in the bottom and the other disciplines in the top. And then I created islands for the different groups that are producing thermodynamic databases. So we have two main islands in metamorphic petrology, the island of Holland and Powell, that's all the groups and collaborators that developed the different data sets and a solution model. It started in 1985 with the first data set, then an updated version in 1990, one of the most popular data sets in 1998, and the most recent one in 2011. And every time you can see that they developed or they published after the data set some compatible solution model. And I just showed a few of them here on the side. At the same time, in the 80s, Rob Berman also developed an internally consistent data set in 1988, and he published some compatible solution models with this data set. There were other data sets that were published, for example, from Chatterjee, but I'm not representing them here because they are not used so much in metamorphic petrology because they are lacking compatible solution models. At the same time, there were developments in other disciplines, for example, aqueous thermodynamics and MEMS. And those groups, they needed to have thermodynamic properties for solids. So in the early 90s, they connected, for example, the aqueous thermodynamic and the MEMS to the data set of Rob Berman. And most recently, there was an upgrade of the aqueous thermodynamic database that is now compatible with the Holland and Powell 1998 dataset. And at the same time, there were some development in geophysics, for example, to model the phase transformation under mantle conditions. In metamorphic petrology, we had other groups that were working to develop specific solution models or to improve the databases based on the data sets of Rob Berman or the one of Holland and Powell. Here, I'm showing an alpha bridge because those models that were developed, they are compatible with the Holland and Powell database, but they were never included in the official database. Now let's move on to the programs. The first type of programs are the programs developed by the authors of the databases, Thermocalc by Roger Powell, WinTwig by Rob Berman. I'm showing a red padlock here because the source code of those programs is not viable. The main limitation, I would say, of those programs is that they are restricted to use the data that are produced by the same group. For example, you can't use the models developed here in Thermocalc. There is a second category of programs that are Gibbs energy minimizers. I give you two examples, Teriac Domino from Christian de Capitani and Perplex from Jamie Connolly. And those have a different philosophy because they can read the data from the different islands. And that's why they are shown as both here on this map. And also, those programs were very important because as they minimized the Gibbs energy, they were also used by other programs. And I reported here a collection of programs that were developed mostly in the past 15 to 10 years that are using the Gibbs energy minimizer. I really encourage you to go through the list. There are amazing programs that can be used to do a large variety of computation using Gibbs energy minimization. And they can also use a lot of different thermodynamic data. So after this introduction, let's move on to the first part of a thermodynamic database. And this is the internally consistent data set. And here I reported an example of the most recent data set from Holland and Powell 2011. Of course, it's just a selection of the phases because you have more than 250 phases in this data set. And as you can see, we have thermodynamic data for each phase, and we have the formation, enthalpy, the standard entropy, some parameters for the heat capacity function, and some parameters for the volume function. Those data sets, they are said to be internally consistent. And this means that all the data reported in this publication, they adhere to one set of reference values. For example, the value of T0 and P0, they are based on the same basic thermodynamic definitions. For example, the equation of the apparent Gibbs energy. And those data, at least part of them, were derived simultaneously, which means that all the data present in the data set are compatible with each other. I reported here a list of the published data set. On the left column, you already know those ones. Those are the paper from Holland and Powell from the 1985 paper, the first database to the most recent in 2011. On the right side, you see the original data set by Rob Berman in 1988. And two other data sets, the one from Chatterjee using a Bayesian approach. I'm going to describe this in a few minutes. And a second internally consistent data set from Matthias Gottschalk. But the problem of those two data sets is that there is no or very few solution models that are viable. So in the end, there is three main data sets that were largely used in the community: the Holland and Powell 1998, the Holland and Powell 2011, and the Berman 1988. Here, this is a table that we compiled with Eric Dursdorf a few years ago for a review, and you can see all the main data sets and the number of phases. It has grown from about 40 phases in the original data set to more than 250 phases today. This is absolutely fantastic. If you look at the elements, the chemical system, it started with a very restricted range of elements, and now it has been extended to many, many more elements. You can evaluate the impact of those data sets based on the number of citations of each data set, and this is quite impressive. But how is it possible to obtain this data set? So for that, you need some constraints. So you need constraints to evaluate the value of the H0, the S0, the parameters of the heat capacity function, and the parameters of the volume functions. And you have different types of constraints. The first type are the direct measurements of a phase property. For example, you can measure the standard entropy by using low temperature calorimetric measurements. You can measure the heat capacity over a range of temperature using calorimetric measurement, or you can measure the volume of a phase at given pressure and temperature using X-ray diffractions. So those are direct measurement of a given phase property. But for some of the phase properties, actually quite a large fraction of them, you don't have access, or we don't have access to direct measurement of the phase property. In this case, we can use an approximation that is based on fundamental relations, for example, for enthalpy and entropy of reactions. I give you a very simple example. One can assume that the formation entropy of enthalpy of quartz is equal to the formation enthalpy of SiO2, and then the formation enthalpy of andalusite would be the formation enthalpy of silica plus the formation enthalpy of alumina. So if you have data for each polyhedride type that are tabulated, then you can use an oxide summation technique to calculate, to approximate the formation enthalpy and the entropy. For the entropy, we have a better precision compared to the enthalpy, and there is this paper from Holland 1989 that provides the table that can be used with a volume correction to approximate the entropy of any phase for which you don't have experimental data. The third type of constraints that we have are the indirect experiments. They are called indirect experiments because they are not really focused on a given reaction phase property. They are based on reaction reversal bracketing experiments. And here is an example for the reaction quartz equal coesite, and one of the original experiments from Boland and Butcher published in 1982. And what you can see are brackets are different experiments. For example, here at a temperature of 600 degrees, at this pressure, low pressure quartz is stable in the experiment. product, and at slightly higher pressure, coesite is stable in the product of the experiment, which means that the delta G of the reaction quartz equal coesite must be zero between this, within this interval of pressure. And it means that if the delta G of the reaction is zero, if you fix, for example, the entropy of quartz and coesite, the heat capacity function and the volume function, then you only have two variables that are the formation enthalpies of quartz and coesite. Of course, you have two variables for those constraints, which means that if you move one, if you increase the formation enthalpy of quartz, it can be compensated by decreasing the formation enthalpy of coesite, and the delta G of the reaction will remain zero. But by adding more constraints, for example, more reactions, the reaction albite equal Jedi plus quartz, here you will have a new constraint on the enthalpy of formation of quartz. So by considering all the reactions at the same time, all the experimental data at the same time, you can adjust the formation enthalpies of all the data set or all the n member in your data set. Let's talk for a second about uncertainties, because this is important if you want to estimate the uncertainty on the apparent Gibbs energy that you calculate for each phase. For the direct measurements, we can reasonably assume that the measurement is subject to a Gaussian error distribution, as shown on this figure. So you have the value and you have an uncertainty. For the approximation, we can also assume that the error, it's a Gaussian error distribution with probably an uncertainty that is larger than on the direct measurement. But for the indirect experiment, it's a bit more complicated. So now we are looking here at the pressure at constant temperature for the x-axis, the probability on the y-axis, and that would be the position of each alpha bracket of the reaction. So for example, that would be the pressure at which quartz was stable in the experiment. And we have an uncertainty on this bracket that is probably subject to Gaussian error distribution. We have an uncertainty in temperature within 1 degree, in pressure within 1 bar, and this results in this uncertainty. We have the same for the second alpha bracket, above which coesite is stable. But we don't know how the error distribution is between the two brackets. And one of the most reasonable assumptions is to say that at lower pressure than the alpha bracket here, quartz is stable. Therefore, the delta G of the reaction cannot be zero. It can be zero between this interval, taking into account the uncertainty, and the second alpha bracket. And in between, we simply assume that the likelihood is as a value of 1. How are the data sets derived? There are 3 main techniques, and I'm going to quickly describe the 3 main strategies. The first one is the mathematical programming. It was used by Rob Berman and introduced by Rob Berman. Here, the small padlock again shows you that the source code is not a variable. And in this case, I'm showing you an example for a given thermodynamic property, for example, the enthalpy of quartz. And you have 2 constraints for this property, an experimental bracket, that could be our quartz coesite experiment, and a direct measurement of the property that we try to fit. In the mathematical programming, each alpha bracket will be treated as a statement of inequality in the delta G of the reaction. For example, at this condition, the delta G of the reaction must be greater than 0. And on the other side, the delta G of the reaction should be lower than 0. And when you fit that, it means that you have a feasible region in which the delta G of the reaction can be 0. And outside, the delta G of the reaction cannot be 0, and therefore you will never have a solution outside this feasible region. So in the mathematical programming, what you obtain is a range of solutions, especially from the statements of inequality. And then inside this feasible region, you can optimize using, for example, the direct measurement. And here, the value would be close to the bracket. But one of the advantages of this approach is that the feasible region ensures the consistency with all the selected data. It's quite straightforward to calculate if you have the right tools, but it requires some preparation and checking in order to make sure that you have a feasible region. Another strategy that was used is the least square regression. was introduced and used by Holland and Powell for all their data sets. Again, the source code is not available. And in this case, they simplified the problem by saying that the weighted midpoint of the brackets, for example, here in red on your experiment, is treated as the position where the delta G of the reaction is equal to 0. And then they can assume a Gaussian error distribution, which is, as we have seen before, not exactly true. And then if you combine all those measurements together, it is easy to minimize the square of the residuals and to converge to a unique solution. But this unique solution does not ensure a consistency, as I will show you in the following. You can extract some uncertainties. Those are pseudo uncertainties because of the assumption on the experimental bracket, but they are extracted from the variance covariance matrix. The third approach is the Bayes method that is based on Bayesian statistics. It has been introduced and used by Chatterjee. In this case, it combines the advantages of the two approaches. For example, each alpha bracket is treated as a statement of inequality, as for the mathematical programming, and therefore you can define a feasible region. But the good thing about Bayes is that you can approximate the posterior distribution within the feasible region. So you can extract a unique solution using, for example, the mean of this posterior distribution, and you can extract uncertainties from the variance covariance matrix. But the disadvantage is that it is more complex to calculate because it requires Monte Carlo mapping in a space with many dimensions, to try to obtain the posterior distribution of your probability function. So there are several challenges behind this fit, and I just want to point out one of the many problems that you may encounter while you are trying to refine, to optimize a thermodynamic data set. And for example, if you are using as Holland and Powell are using in the least square regression, what they do is they fix the standard entropy. They fix the parameters of the heat capacity function and the parameters of the volume function, and then they refine, so they adjust all the enthalpies simultaneously, and they extract these uncertainties. But the problem by doing that is that if any of the other property or any function holds a large uncertainty, then the value that you will obtain for the enthalpy might be incorrect, and this error will propagate to the uncertainty of your enthalpy values. Here, I'm showing you an example for the reaction carbonate equals pseudoite plus quartz. Pseudoite is a low temperature and low pressure chloride. Those are experimental brackets from experiment by Vidal et al. 1992. And you can see that if you take the Holland-Powell 1998 dataset and you plot this reaction, you will obtain the curve here labeled as 1. And as you see, this curve is not going through the brackets. Now, if you try just for this system to optimize the value of the H0 to try to fit this experimental constraint by simply looking at a very simple system with 3 phases, then the optimal solution from a statistical point of view is shown as reaction number 2 on this figure. And you can easily see that this is not satisfactory enough. And yet the problem stands in the parameters of the CP function. So if you adjust the parameters of the CP function along with the enthalpies of pseudoite, then you can have the reaction going through the experimental brackets. So this is something that can happen in least square, that you have this kind of problem and you do not realize because you do not have the constraint on the delta G of the reaction. If you would be using a mathematical programming or Bayes for this specific example, there will be no solution by using 1 because you will have no feasible region, or the reaction will not go through the feasible region that is defined by the experiments. And there are cases for which this kind of error remains undetected. So this is the end of the first part on the internally consistent data set. And now we are moving on to the second part on the activity models. So activities are values that describe how reactive a particular n-member component is for a given mineral composition. Activity values may range between 0 and 1, as shown on this diagram. So the y-axis here is showing the activity. An activity of 0 means that the component is not present in any amount in the solution, and an activity of 1 means that the component is pure. This is an example of activity composition relationships for plagioclase at 700 degrees, and the continuous lines show the real activities for albite and anorthite in a binary diagram that were determined experimentally. And the dash lines here on this diagram show the activity of anorthite and albite if plagioclase would behave as an ideal solution. And in this case, simply the activity of a component will be simply the fraction of this component. So the activity of anorthite for this composition would be 0.4, the activity of albite would be 0.6. It is important to notice that in the case of plagioclase, unless you are very close to an N member, such as anorthite or albite, then the activity or the reactivities of the N members will be greater than what is predicted by ideal mixing. So we need an excess energy to explain this difference. So let's take the example now in a diagram with the molar free energy on the y-axis. Let's assume that we take 1 mole of plagioclase or 1 mole of albite, 1 mole of anorthite, and we mix them together. The energy of one N member is here, the Gibbs energy of the second N member is here, and the energy of the mechanical mixture is simply the linear combination of the two N members. So it would be exactly in the middle on this curve. If now, for a given pressure and temperature, you have a reaction, and from this mechanical mixture, you form one phase, you form a solution. Then the energy will decrease because you have the entropy of the new solution that will increase. So the difference here in energy is this term, the minus T delta S, the delta entropy of the solution. So the energy will decrease, the Gibbs energy will decrease. And this is the case where the G ideal is shown by the blue curve here in this figure. For some cases, the G real, shown here as the green curve, is above the G ideal, which means that to get from the G ideal to the G real, you need to have an excess function. The excess function is shown in red here on this diagram. So by adding the G ideal plus the G excess, you obtain the G real of your solution. So you have an ideal contribution, a non-ideal contribution, and that will give you the G real. So the excess energy can be estimated. For example, the magnitude here of this curve above the mechanical mixing is controlled by 3 parameters, and those are known as a Modulus parameter. There is the WH, the Modulus parameter, that is temperature and pressure independent. Then we have a WS that is temperature dependent, a WV that is pressure dependent. And you can calculate the WG, that is simply the sum of the 3 Modulus parameters. Now you need to formulate the model not only for a binary join between 2 N members, but between all the N members that you have in your solution. And there is a very elegant formulation that is the asymmetric multi-component formulation by Holland and Powell 2003. I just gave you here the equation to show you that the excess energy for any binary will be controlled by the Modulus parameter. This is this term here. There will be the proportion of the N member, so the composition. And then you have a size parameter for each N member that will control the symmetry, so the asymmetry of this function of GXS. It's worth to notice that if you have a simple solution models and you use this formulation, if you have 5 N members, for example, in your solution models, you will need at least 10 Modulus parameters if you have no pressure and temperature dependency. And you will need up to 30 Modulus parameters for this simple model if you have a temperature and pressure dependency for the non-ideal contribution, for the GXS. If you take one of the most recent models from Green et al. 2016, the Kleiner amphiball, you have 10 N members in this solution model. This means at least 45 Modulus parameters if there is no temperature and pressure dependency. But in this specific case, there are, and you can go up to almost 150 parameters that need to be optimized. Plus, of course, the size parameter for each binary that will control the asymmetry of the solution. So you sum up and you have many, many parameters that need to be optimized for a single solution model. And this is why up to now, the set of solution models are developed as a second step and they arrive after the data set. If we take the example of the Holland and Powell data set, it was published in 2011, and then you have a first paper with a set of solution models for metapilite from White et al. 2014. Then you have a new paper with a set of solution models for metabasite from Green et al. 2016. We have seen in the previous part that the data set is mostly based on the experimental data, but for the solution models, we have so much parameters to fit that it is impossible to fit them only based on the few experimental data that are available. So they are complemented with natural data and in some cases by guesstimates. What I call guesstimates is a behavior, for example, of the solution model that you would expect. So the presence of this stability field for this bulk composition. And you can use this as a constraint while adjusting the solution models. In practice, there are several parameters in each solution models that are not optimized using an algorithm because there are too many unknowns for not enough constraints. But those parameters can be parameterized. For example, if you can assume that along an iron magnesium binary join, the excess function will be the same, or the behavior will be the same on a tetrahedral site, for example, in chloride or white mica. And by doing this exercise, you can parameterize some of the Modulus parameters. But most of them are manually adjusted by trial and error and often based on guesstimates. So now this is a very challenging task, and it's quite impressive to see the success of those databases when we realize the size of the problem. And I want to show you an example to illustrate some of the numerical techniques that can be used to fit complex excess functions. This is again a binary. We are looking at the G excess. The position here at 0 on each side is the dataset n member. That's the G of the dataset n member. There is no excess in this case when you reach the n member composition. And this is inspired by the pyrobrossular join. And the squares here represent hypothetical calorimetric data with their absolute uncertainties. Of course, it's rarely the case that you have so good constraints. But in this case, you can see that there is a jump in the excess function for a composition of A about 0.7. So you can't really fit that with a symmetrical excess function with a small Modulus parameter or with a large Modulus parameter. You cannot really fit this excess function with an asymmetrical model as well. So you need to have something a bit more complex. One of the strategies that can be used has been introduced by Darkens in 1960, and this is known as the Darkens quadratic formulation. The idea is to divide the binary here in the solution into two terminal regions, two main terminal regions, the one here on the right side, the two on the left side, and the third one that would be exactly at the contact between the two terminal regions. And then what you can do is to fit the function, the excess function in the terminal region 1, you can use the dataset n member here, the G is 0, and you can change the G of the other n member on the other side, because you will always use this model in the terminal region 1. You can do the same for the second model. You use the dataset n member, the energy of the dataset n member here, and then you adjust the position. You create a virtual n member on the other side that you change its energy, and this gives you the flexibility to fit complex functions. But the problem here that you have several solution models for the same mineral. And this is not compatible with Gibbs energy minimization because, for example, in Perplex or Tiriac Domino, you would need to have two solution models for your mineral, and for a mineral composition at 0.7 here on the mole fraction of A, of course, solution model number 2 would be more stable than the 1, whereas the 1 has to be used in this terminal region. So this solution is elegant, but not satisfactory enough for Gibbs energy minimization. Another strategy could be to create a new N member that is not in the data set. And then you can calculate the Gibbs energy of this N member by using a linear combination of the dataset N member plus an excess energy that is shown here by the red arrow. And then you will have two new binaries between the different N members, so B and C and A. And then you need to have more Modulus parameters. I call this Pseudo DQF type 1 because the DQF refers to the Darkens quadratic formulation, and this is not sensu stricto the Darkens quadratic formulation. But this amount of energy is known as Pseudo DQF, and we call it type 1. There is another type of Pseudo DQF correction that you can make, and in this example, you change the energy of your dataset N member. So for example, here you change the energy of the N member A and you change the energy of the N member B. And this gives you the flexibility to fit a more complex excess function. So that would be the most satisfactory solution in this example. Remember, that's an hypothetical example just for illustration. But the problem is that you change the energy of your dataset N member. And the G of the dataset N member was optimized based on experimental data. And this might cause some problems. So now we have seen that there are two parts in a thermodynamic database, the dataset and a set of activity models. And now I'm going to discuss quickly both together. So in what we call a thermodynamic database. And if you pick a data set, a set of compatible solution models, then you can calculate one of these pressure, temperature, mineral assemblage diagram, also known as phase diagram or a pseudo section. This is a simple example of them. But for that, you need a thermodynamic database. So as I told you, the strategy is first to publish the data set and then the solution models. This is an example for the Holland and Powell 1998 data set with a list of all the solution models, all the papers that were published over the years by the group of Holland and Powell. And as you can see, every time that there is a new paper with a new solution model, this means that you have a new database. It's always based on the same data set, but you create a new database. And in some of those models, some standard state properties were also adjusted to be able to fit some complex excess functions. And there are also the non-official solution models that are compatible with the same data set. So when you mix them together, then you create a new database. So virtually, we have several databases, too many databases, and this is actually a problem that in every paper, almost, we have a slightly different database. So the internal consistency, as I defined here, in all those databases that are available, is usually not rigorously tested by the users of the thermodynamic programs. And this can be a problem from time to time. Now, to show you some of the challenges, I want to take an example on the most recent data set, the DS62 from Holland and Powell 2011, and speaking one of the metapilite model from Richard White, the biotype model. You can see here that we have 6 N members in this biotype model, and 3 of them, the RD biotype, the titanium biotype, and the ferry biotype, are not present in the original data set. So you need to build that. You need to calculate the apparent energy of those non-dataset N members using an alternative strategy. And you can use this pseudo DQF type 1. What you simply need is for each of them, you need to write a reaction. For example, the RD biotype is a linear combination of anite and phlogopite. So you can have a reaction 1 RD biotype equal 1/3 of anite plus 2/3 of phlogopite. And translated in terms of Gibbs energy, you simply say the Gibbs energy of RD biotype equal 1/3 of the Gibbs energy of anite plus 2/3 of the Gibbs energy of phlogopite plus the DQF parameter. That's the pseudo DQF type 1 parameter, and in this case, 2 kilojoule. That allows you to move the N member RD biotype away from a linear combination in terms of Gibbs energy. You do the same with the ferry biotype, but in this case, you need a ferric N member to write the reaction, and there is a reaction that andradite, that is a garnet, a ferric garnet, plus histonite equal ferribiotite plus grossular. And again, there is a pseudo DQF type 2, type 1 parameter of 3 kilojoule. And then the titanium biotite is also calculated to keep energy from a linear combination of phlogopite, rutile, and brucite, plus a large pseudo DQF type 1 parameter. So that's the way the solution model of biotite is constructed and then used to fit. But in this case, they had some problems, especially to fit a well-constrained biotite breakdown melting reactions that otherwise would occur at unreasonably low temperature for FeO-rich biotite. This is taken from White et al. 2014. And they added a DQF parameter to the anite N member. And the anite N member is an N member from the data set. So this is the pseudo DQF type 2, where you change the energy of a data set N member. This is a small amount, 3 kilojoule, that is added. So you change, and then you can fit a more complex function. But the problem is that in this case, the solution model will affect, in some sense, the internal consistency. So it's good because at least you are sure that the model will fit the well-constrained melting reactions in the system, but you might have some reactions that you used to fit the data set that are no longer fitted. And I show you here one example to justify the need to check the database against the experimental data. I generated this plot using the program Therion. That is a program that will be distributed, I hope soon, with Taiyak Domino, and it allows you to check thermodynamic database against experimental data. This is a program from Christian de Capitani and Rob Berman. Here on this diagram, you can see the experimental brackets for the ln of Kd iron magnesium partitioning between biotite and garnet. And those are the data here from Ferri and Spear, and they are shown as rectangles because the uncertainty is taken into account. And then I plotted the ln, the Kd function using several databases. The TC55 with the White et al. 2007 model, the Berman database, the TC55 with a special biotite model from Lucy Tachmanova, and the TC62 from White et al. 2014. And you see that the DQF value of 3 kilojoule puts this reaction out of the experimental constraints. Of course, it doesn't tell how it doesn't affect how the biotite composition will be in your solution model. If you have an intermediate biotite composition that is not an N member, here we have the anite in the reaction, then of course this will not have effect because that's the function that is fitted. But if you go too close to the N member, to the anite composition, and that's exactly the case for those experiments, then you will have this shift. You can also compare the data to experimental data yourself, and there are some authors that started to do that, and I think this is really great to have this kind of test. This is a recent publication from Gervais and Entropies in 2021 in Contribution on Mineralogy and Petrology. And here, what you see are experimental data from Patino, Ducey, and Johnson. Those are melt-bearing experiments for metapelite, and each dot here shows the result of the PT condition of the experiment. And then the author, they calculated the phase diagram using 4 different databases. DS55, 5.5 with the White et al. 2007 model, DS62 with the more recent models, the DS5.5 with the Lucy Tachmanova's model for biotite, TCC in Perplex, and let's say a database that is used by the Perplex user that combines a very simple model for plagioclase, for example. So you can see the results of the comparison. Every white dot means that the observed assemblage is reproduced by the diagram. And as you can see, this is not often the case. We can also look at the biotite composition. This is the Ng number for the biotite on the y-axis against temperature. The results of the experiment are shown by the continuous curve at 0.7 GPa, the dashed line at 1 GPa. And you can see how the models, the different databases will plot the composition of the biotite that are predicted to be stable for these conditions. And you can see that there are significant differences between the databases. To finish with the thermodynamic databases, I want to emphasize that most of the efforts were done to optimize the calculation of the apparent Gibbs free energy, because that's what we need to draw our phase diagrams. But now there are more and more disciplines, other people that are needing this thermodynamic data, and they try to estimate or to use the databases to estimate values of other thermodynamic properties. You have to be aware that if you do that, it would be good to check always against experimental data, because remember again that everything was optimized for the apparent Gibbs free energy. This is a very nice example from Durostov. He worked a lot to estimate the volume of the phases at different pressure and temperature conditions. And he showed, for example, that the Berman equation of state for volume has an unphysical parabolic behavior above 3 to 4 GPa, because the database at the beginning was optimized for lower pressure conditions. I'm showing you one more example quickly. This is an example for the Entropies data. Again, the diagram was generated using Therion from Christian de Capitani, and it shows the values of the entropies measured in experiments. That's the squares here, the data from Holland and Powell, the red dots, and this is normalized to the Berman values. So it means that all the entropy values for the Berman database for all those in member are along the midline here. On the left side, you see that there are data or N members for which the entropy values of Holland and Powell are perfectly fitted on the experimental value. Berman has a bit more flexibility to be within error, because in the mathematical programming and the approach of Rob Berman, the entropy is also adjusted together with the enthalpy. Then you have a second category for which the experimental data are contradictory. And in this case, often the database will be in between the two values of the experiment, as it is the case here for anorthite. And sometimes for firelight, for example, one experiment was favored by the authors to select, to fix the entropy values. So this is something you have to be aware of, and that's why it is recommended to check and to plot the values that you obtain from the databases against experimental data. And there are other N members for which you have significant differences. For example, kyanite and andaluzite, where the Holland and Powell data are based on old experimental data. There is a new year experimental data that are available that are not fitted in this case. Again, this is no problem, because the main interest is the Gibbs energy. So the small uncertainty on the entropy value will be propagated on the enthalpy value. But you have to be aware of that if you want, for example, to estimate the entropy values of your N members. So to conclude, I want to try to give you a few perspectives. Today, it's amazing. I have to say, it's really stunning how much the databases have changed our discipline. For example, in metamorphic petrology, we are using phase diagrams to do thermobarometry, to predict many things, but also there are several applications across the geosciences. Now we can use the databases to estimate densities, to be using the mechanical models. We can model mass transfer using reactive transport modeling. We can model element cycle, crustal recycling, or many applications. So it's not only the metamorphic petrologists that rely on the thermodynamic databases. So if we want to go to the next step, then we need to have new constraints. We need to have more constraints to fit the next generation of thermodynamic databases. One of the ways to take is to use first principle physics, such as ab initio modeling, to try to estimate, to bring constraint on the standard state properties. This is an example from a really recent paper from Benisek and Dak 2018. And what they did is they estimated the enthalpy of formation of several phases, a list of about 15 phases in this paper, using density functional theory. This is a computational approach that is based on quantum mechanical modeling. So what you do is you calculate the formation enthalpy from the elements. From the elements, you can go to the oxide using the GenF table, and those are high accuracy calibration of the formation of the oxide from the elements. And then from the oxide, you can use the density functional theory to calculate the formation enthalpy of forsterite in this example. So the authors, they did that for several phases, and then they plotted the differences between their small database and the Holland and Powell data. You can see that the differences are very small. It's about 1 kilojoule per mole in the value of delta H0 for forsterite between Berman, Holland and Powell, and the new value here. But it can have a dramatic effect on the position of reactions. For example, pyrop equal kyanite plus quartz plus H2O is drifted in this case by about 200 degrees if you use the enthalpy values from the density functional theory. The second type of model, ab initio modeling, can also be used to estimate excess function. And this is an example from a paper from Benoit Dubac, where you have a binary joint between muscovite here on the right and pyrophyllite on the left. And what Benoit did is to generate some structures of supercell for different composition along this binary joint. So it generates the structures for each composition, and then it estimates the energetic state and the degree of ordering of the most stable structure. So this requires Monte Carlo simulation to generate the structures. And then the energetic state and the degree of ordering can be established. So you can infer the energy of mixing along the binary, and that's all the stars that you see here. So you can fit the excess function based on those data. And this is fundamental because it means that for this binary, you have a very good constraint on the excess function. But this is one binary in one solution model that is a white mica in this case. And this is a very intensive calculation to end up with this data. So we need to do that more and more. So to conclude, I have to say that a terrific job was done to develop the databases. But today, if we want to go further, we will need more primary data to fit the new generation of databases. We can use ab initio modeling. I have shown 2 examples, and there are more to come. We essentially need more experimental work. And to do that, we need to encourage people to run experiments. And one way to do that would be to change citation policy for the experimental work. We need more acknowledgement in the community. You imagine some key experiments that are cited once by the data set, the people doing the data set, and then the data set would be cited by the author. So we need to find a way to acknowledge experimental work. And I encourage you to check when you use a thermodynamic database on which experimental data the data you use are based on. And then you might want to cite the experimental data. If we want to derive a new generation of databases, I think that one big goal would be to derive the standard state properties and the activity models together to ensure internal consistency through the entire process. And this would require new optimization and minimization routines. And ideally, those minimization routines or optimization routines should be used on bias to try to derive robust values and uncertainties. And I think one of the challenges would also be to provide an open source tool that can be used when new experimental data become available. Finally, we definitively need to test more the existing databases. And for that, it would be nice to develop a database of experimental data that a program can read and plot and to compare to test a given database. For that, we would need to provide an open source tool to easily test any database against experimental data and to encourage the users to perform those tests. So this is work in progress with this Therion program, and I really hope that it will be soon available for the community. Then to be a bit provocative on my last slide, I would say that if and only if a database satisfies the primary constraints on which it is based, then we can think of using the thermodynamic models for thermobarometry. We can run one of the models using the programs that are available. For example, Dave Water will talk very soon about thermocalc, and tomorrow we will have two talks. The first one from Mark Caddick about Perplex, and the second one from Doug Tinkham about Tiriac Domino. Then we can apply the models to more complex situations, and Dave will give you some recommendation for the best practices in phase equilibrium modeling. We can also address more complex situations where, for example, the entire rock is not reacting at the same time, or when we extract components, this will be the token reactive bulk composition. And then we can ask ourselves some of the most important questions. What is the influence of kinetics? All those databases are based or are used in a framework of equilibrium thermodynamics. What happens if this is not the case in nature? And to know that, one way could be to try to see how good are the models that are produced at reproducing the natural pattern. And Dave Pattison and Jacob Forscher will talk about that. So with that, I thank you for your attention, and I'm happy to answer questions.
Well, I'd like to thank Pierre for an absolutely superb overview of a very complex topic. And I'm sure that there are some questions that he'd be very happy to entertain. So the procedure at this point is that there have been some questions submitted, and I think that Jacob will be posing the questions to Pierre, and I think he will probably be in a position to answer most of these, but the other participants in the presenting group will also be able to contribute as necessary. So at this point, I'd like to turn things over to Jacob, and who might have the first question for Pierre.
Thanks, Dave, and thank you, Pierre. That was a great talk. So yeah, thank you for everyone who posted questions throughout Pierre's talk, and for those of you that keep them coming in, we'll try and get to as many as possible. I'll try and consolidate them down so that we can, I don't know, get through these things. A lot of people asking Pierre about internal consistency. And so I thought, and perhaps you covered this quite quickly, but what are the criteria to say that a data set or a database is internally consistent? If you could recap that before we go into the other questions.
Well, thank you. It's a great question, and I have prepared a slide for that. I jumped on the concept a bit quickly because I saw that you need to understand each part before to really discuss the importance, or to be able to evaluate the importance of internal consistency. So those are some conditions. They are not from me, they are from Martin Ingir, and they were published in 1992. And they mostly concern the data set, but I would say that they are also applicable ultimately to the solution models. So I already told you the first criteria is to adhere to one set of reference values and to the same basic thermodynamic definitions. I think this is the basis. It is fundamentally important. And then Martin came up with the second criterion, that is that the database should represent all the listed experimental data in the sense of the best compromise. So this is the simultaneous fit of all the data. And at this stage, it's regardless whether the data are compatible or if they are conflicting. And I think I showed you a few examples, for example, with the entropy, where you have a conflicting experimental data. And in this case, the database should try to find the best compromise. And then the last point that is also very important is the compatibility with all the underlying data within the stated uncertainties, except for those data excluded in order to achieve a consistency with the rest. And this one is one of the most important. It means that the database at the end should satisfy, or should really satisfy, be compatible with all the experimental data it is based on. And Martin came up saying that if point number one is a satisfied database is formally consistent, if point number 1 and 2 are satisfied, it's partially consistent. And if only the third, or if the 3 criteria are satisfied, then the database would be fully consistent. But it's mostly today applied to the data set, I would say.
That's great. I think that answers. There were some nice questions in the Q&A about, will we ever achieve true internally consistent models? And I think you've answered those of these differences between the, pulling all this data together from different bulk compositions, laboratories, et cetera, and just looking at the overall. Then somebody asked about if some of the n-member properties of these, when you're looking at the solution models, they're derived from combinations of others. What does that mean? Does that mean that the database is formally tied to those chosen solution models? And then, does that mean that they have to be used when you're analyzing rocks if you're going to try and preserve that internal consistency? And perhaps you've sort of covered this here, but yeah, linking again the data set to the solution models and how you keep internal consistency. That's the question.
Yeah, no, it's a very important question, and it's a complex answer, but I can put it that way. When you derive the data set, mostly the constraints are on the n-member, so the Gibbs energy of the n-member, which means that you don't need to have complex solution models to satisfy the set of experimental data. There are, of course, for some phases, some simple solution models, for example, for autopyroxenes, which means that then when the complex solution models come after that, of course, the authors have to make sure that the model will still satisfy the primary constraint. But basically, for most of the data set, you do not need, in theory, complex solution models.
Okay, and then a couple of people asking about, you mentioned Therion or Therium as a program that you were using. You would use that for optimization of the databases and the solution models, or only to check it?
So at the moment, Therion can only be used to check the database. So to plot the functions and to plot the experimental data together. Of course, what you can do, and this anyone can do it, is simply to use Theriac as a Gibbs energy minimizer, or to use a Perplex to optimize the database. And yes, this is possible.
Excellent. Another question here talking about your the GXS functions and some of the DQF parameters applied and the different pseudo DQFs. And it asks, could you comment on the atomic scale mechanisms that cause those significant jumps in GXS that have to be fit by these DQF adjustments? Which phases are they most significant for?
Not really. That goes far beyond my competencies. And if any other presenters have something to say, I'm happy to give the question. But what I can say is that I'm really looking at that on the fitting point of view. How do we extract the database? And no, I can't really comment on how do we obtain such complex excess function. That goes far beyond my skills. Sorry.
Oh, that's perfectly fine. You have to have the answer to everything. Okay, another one here. Where do we learn about the aspects and procedure of this mathematical modeling and how we can apply it to, what I think what you were talking about at the end in your conclusions and to the thermodynamic data sets and databases?
Maybe this one, the ab initio modeling.
Yes, sorry. I think that's what they're getting at. The ab initio modeling. How would you go about that?
It would be wonderful to have the most important binaries for the most important solution models to be studied using this ab initio modeling. But this is a lot of work for a single modeling. I can, for example, for this specific paper, I can say that this is a good part of a PhD work to try to just obtain the excess function for this binary. And this is amazing. I mean, it's very important data, but it's a lot of effort, a lot of computations. I mean, imagine you have to generate a lot of supercells like that and then calculate the energy of the most stable structure. This is a lot of effort. And there are many challenges on the computational side.
Excellent. Yeah. Okay. Another question here asking about often, in more recent years, they still see Holland and Powell 1998 cited in post-2011 papers where they could have used Holland and Powell 2011 from the data set point of view. Is there an advantage of using one over the other, in your opinion?
I don't think there is an easy answer to that one. I would simply say, and I think that one of the goal of the workshop is to show this, or to discuss over several talks this complexity, the complexity of this answer. And I would simply say that for very simple systems, the old data set would do the same job as the new one. If you need more fancy elements, and this comes back to the table I showed at the beginning, if you want to run a model, for example, with let's say nickel, copper, or chromium, or elements like that, then yes, you need to use the most recent data set. But for me, there is no problem to use an old data set, an old database, provided that you can model the composition of the phases you obtain.
Yeah, that's an excellent answer there. Another one here that isn't a question, but a nice comment about you were talking at the end about advances in experimental petrology and where we need to go in order to build up these data sets once again. And talking about the funding system also needs to change, starting with more acknowledgement and opportunities for this kind of work, kind of talking as you were talking about the citation policy. The excuse is that this is not impactful work, but as you clearly demonstrated, we need to keep improving the thermometric databases to better investigate geological processes. I thought that was a really nice comment that ties in with yours.
This is fundamental. Without experimental data, there would be no thermodynamic databases and there would be no applications. So I think this is really important. And yes, the funding is important, but unfortunately, funding is too often relies on citations.
And then again, relating to the experimental, in your opinion, what are the most needed experimental data that are still missing from the database? What would you do first? That's a bit of an open question, I suppose. But
I don't know. I don't know. I haven't done a database, an entire database myself, so I can't really answer this question. I have tried a few small problems to solve a few small problems. There are several solid solutions. I think we are missing quite a lot of constraint on the solution, on the solid solution side. And for the data set, I can't really say, but how much we miss for the, or what do we miss for the, to constrain the data set. But I can maybe just show you, if we have a minute, one diagram that I prepared at the end. And this diagram here shows you the fraction of experimental data that is used for fitting the data set in the most recent data set of Holland and Powell 2011. And you can see that only 5% of the data they used in 2010, 2011 were published between 2006 and 2010. 10% were published between 2001 and 2005, and a bit more than 50% between 1996 and 2000, which means that only 30% of the experiments were produced since 1996. And this is quite amazing to show that there is a huge problem in the decrease of constraints for the databases, to fit the databases.
Okay, and this comes back to your idea at the end of collating all of this experimental data and having a list of it that then we can identify, as that question just asked, which phases do we need to target first for further experiments. Okay, excellent. All right, well, we've got a time for a couple more. Considering the composition of a phase affects its behavior away from ideal behavior, should the composition of the phase in my rock decide which solution models I use? And I think this is referring to your DQF slides and talking about, should I be specifically changing the model depending on the composition of the phase?
Let's say, of course, the most important point is that the composition of your phase, you should be able with the model to access this compositional range of the phase that you observe. So for example, if you have a large amount of titanium in your biotype, then you need to have a titanium end member to be able just to model properly the phase that you observe. So yes, in a sense, yes, absolutely. There is a dependency between the model that you select and the composition of the phase that you have. Yeah, and then we know that some models behave better for high temperature mineral assemblages, and some other models would behave better at low temperature.
I think that's a good answer. And leading on from that, somebody asking regarding these kind of GX functions, why are they only fit using parabolic functions? Why do they not use higher order polynomials to fully capture the data as they change across these? And I think you've got a good example shared there, Pierre.
Yeah, the answer is pretty in my opinion, quite simple. It's about the complexity. Yes, it is complex, but you need constraints. So to fit it, to really be able to fit a complex function, then you need to have some information on the shape of the function. Otherwise, you can't really fit it. And I would say that in my experience, you can reasonably fit most of them using this kind of formulation. I'm not sure it will be perfect, but you can approach a reasonable solution. And let's face it, if we take the most recent database, the most recent solution models, somehow they are very close to a satisfactory solution. So they manage to fit those complex functions.
Excellent. And another nice comment that's just come in here talking about not only do we need to perhaps design and do new experiments, but revisiting some of our known experiments in that, you know, people looking at the work of on Garnet and Biotite from Ferry and Spear in their classic 72 paper. It wasn't perhaps exactly a solid solution between pure anite and phlogopite. And if there's some aluminium and things mixed in there, you've got an extra component to account for. So perhaps that's another avenue that we can explore.